The transmission lines connecting our cities and industrial centers share a specific architecture. They run on an ungrounded three-wire configuration. This three-phase alternating current provides the continuous torque required to drive massive induction motors without the vibration or stalling inherent to simpler systems. If polyphase power is the mechanical requirement to run heavy industry, it raises a question of optimization. If multiple phases are better than one, there must be a specific reason the global standard remains at exactly 3. Two-phase power was developed first. It successfully powered early electrical grids, but hit a physical ceiling preventing it from scaling to modern industrial demands. Three-phase power represents the mathematical optimum for alternating current. Operating at 120-degree offsets, balances continuous mechanical force with the absolute minimum conductor material. To understand the optimization, we start with a single-phase generator. A rotating magnet passes through a single loop of wire. As the magnetic field approaches and then passes through the coil, it induces a voltage. The intensity of the magnetic field changes as the magnet approaches and recedes. This pushes and pulls electrons through the wire, creating a synchronized sine wave pattern for both the voltage and the current. The instantaneous voltage at any exact millisecond is dictated by the angular frequency, the speed of the rotor, multiplied by the time, as shown in this equation. By multiplying the voltage and current values together, we can plot the instantaneous power. This curve tracks the actual energy being delivered to a load at any given moment. Because the voltage and current values rise and fall together, they cross the zero axis simultaneously. This means the energy delivered by a single-phase system drops to absolute zero twice per cycle. This pulsating power profile is sufficient for a light bulb, but an industrial motor requires a different mechanical input. A single-phase magnetic field does not rotate. It only flips polarity back and forth. If you supply this current to an induction motor, the rotor receives no directional push and will simply vibrate in place. This makes a single-phase system incapable of self-starting large industrial loads or providing the constant mechanical torque needed for heavy machinery. Engineers addressed this by adding a second set of coils to the stator, physically offset by 90 degrees. This second coil experiences the magnetic field a quarter cycle later, producing a second set of voltage and current waveforms. When we mathematically combine the outputs of both phases, the pulses overlap. Because one phase is at its peak while the other is at zero, the total instantaneous power becomes a flat, continuous line that never drops. This exact 90-degree delay creates a rotating magnetic field, allowing motors to self-start and run with constant torque. However, this solution introduces an economic bottleneck. Doubling the power phases in this configuration requires 4 individual wires, which doubles the material cost of the transmission line. Combining the 2 neutral return wires to save material creates a thermal hazard. Because the currents are out of sync, the shared wire must carry a higher combined load than the supply lines. Safely managing these overlapping currents requires a disproportionately thick shared wire, which limits the potential savings in copper or aluminum. Two-phase power solves the mechanical problem of rotation, but the requirement for 4 conductors makes it economically inefficient for long-distance distribution. Three-phase power utilizes 3 sets of coils separated by 120 degrees. This configuration produces 3 intersecting sine waves. The voltages and currents are evenly spaced across the cycle, ensuring there are no gaps in power delivery. The total power is a straight, continuous line. Mathematically, the combined output is higher than the individual peaks of any single phase. The primary advantage of the 120-degree offset is found in the timing of the 3 current waveforms. In a balanced load, if you sum the current values of all 3 phases at any exact moment, the result is 0. This happens because the magnitude of one phase is always exactly offset by the other 2. Because the currents always sum to 0, each wire effectively acts as the return path for the other 2. This allows engineers to completely eliminate the neutral wire from the transmission system, reducing the number of conductors from 4 to 3. We can compare the efficiency of these systems by mapping their total power output against the required material weight. By eliminating the neutral wire, 3-phase delivers 50% more power than a 2-phase system while using 8% less material. Compared to a single-phase system, Three-phase requires one additional conductor, a 50% increase in material, but delivers triple the total power. Adding a fourth or fifth phase would require even more conductors, without providing a corresponding reduction in return path material. The 120-degree offset is the specific geometric point where material savings and power delivery are most efficient. This mathematical model scales to the high voltages used for long-distance grid transmission. Transmission starts with a delta configuration. The coils form a closed triangular loop that operates with just 3 wires. This leverages the zero-sum current math to omit the neutral wire over massive distances, which minimizes weight on the towers and reduces infrastructure costs. The layout changes at the local substation, where the grid must supply individual homes. The transformer secondary uses a Y configuration. This adds a central point where a neutral wire is tied, providing a return path for the unbalanced loads typical of residential properties. Because many residential pole transformers connect to 2 of the 3-phase conductors, it is often mistakenly assumed that homes use 2-phase power. The transformer's primary coil only reads the single difference between those 2 conductors. This effectively converts the 2 out-of-phase sources into a single-phase connection. A center tap on a secondary coil splits this single 240-volt wave into 2 120-volt lines, providing standard power for home appliances. 2-phase power was a functional attempt to overcome the limits of a single coil, but 3-phase remains the global standard because it optimizes the physical relationship between trigonometry and material cost.